the weather is getting cold. So it looks like the winter is coming up quickly. So please stay healthy and stay safe, because so I think the many students are vaccinated, but the COVID-19 is spreading fast. So that's the problem. So please stay healthy. That's important. Okay, so let's start today's class. So actually in the previous class, we learned about the, oh, why is it so large? So in the previous class, we learned about how the file systems can be implemented on the block-based storage devices. So we learned that actually our computer systems are composed of sorry. So so sorry. So actually our computer systems are composed of many abstracted layers. So that means that, so there are many layers in the computer systems, and then between layers, the detailed structure or detailed operation, and then some detailed behavior of the lower layer is not revealed to the upper layer. So actually the interfaces are just revealed to the upper layer. So to the software, that means the operating system think that the storage devices are just a block-based devices. So that means the access latency to each block is nearly similar if the storage devices are block-based memory devices, but it's not true. So we learned that we learned about the architecture of hard disk drives and solid. Actually, briefly, we learned about the architecture of solid state drives. And then especially for the hard disk drives, the access latency for block, a certain block is, is not constant. So it varies by the location of target blocks. That means the target sectors actually. And then even though the flash memory, so SSD used the flash memory as storage media. So actually that means the flash memory is the solid state memory devices. So it is different from the hard disk drive, because hard disk drive has some mechanical parts. So in order to access a certain location of data, then the motor need to rotate, and then also the arm, and then the arm needs to move around on the surface of the hard disk drive. But this detailed operation is hidden to the upper layer, that means the operating systems. So the operating systems can give very simple commands like read, write, erase a certain blocks onto the storage devices. Also, the operating systems provide the one more abstracted layer called file system. So file system is just it's a software layer, and then actually the users access stored data on the storage devices using files. So, and then we learned about the Unix-like file system. That means that the file is, that means the group of data, the data blocks are indexed by some index structures. So in order to access the certain file, this file location should be get figured out from this indexed structure, like some database systems. And then if this location is figured out, then operating system just access the certain data blocks on the storage devices. So actually, we think that we just think we can think that the data stored on the storage devices can be accessed by block numbers, or block addresses. But actually, in order to get the certain this block addresses, then we need to access some index structures. So that's why we need additional accesses to read or write data to files. Okay, that's what we learned in the file system. Okay, the problem is that this detailed architecture, so then the detailed behavior or detailed characteristics of storage devices are hidden to these software layers like file systems or operating systems. So what's the problem? The detailed characteristics of this low layer is hidden. It's hidden. So, and then the operating system just gives very simple commands like read, write, and erase a certain blocks or sectors. Well, what's the problem? This command, so actually the software side view, if the command is given to some devices like hardware, then the response comes from the target hardware. But usually, the software does not consider about the latency. So latency can vary by some conditions or that means that includes the location of the data. So, but usually when this command is designed, this latency is not considered. Okay, that's so this detailed behavior is hidden, so the performance can be degraded by this simple command. So why? So actually the operating system can give some read. So certain sector number 1, sector number 2, sector number 3. But the location of this sector can vary inside of the storage devices. And then based on this different stored location, the access latency can be different also. And then if the access state latency is so long, then the performance can be degraded. So that's the problem. So actually, as the operating system just has a limited information to the lower layer of the devices, then this lower layer need to provide some best performance or some management method to provide some better performance to the upper layer. So that's why the hard disk drive or solid state drive has a firmware architecture, that is the software part, and then this firmware just manages the storage media such as the player of the hard disk drive or the flash memory of the solid state drive. Okay, so actually the firmwares inside of these storage devices consider some performance issues. Okay, and then in order to increase the performance of the storage devices, we need to know the characteristics of a certain storage systems. And then that's always true for other systems. So in order to increase the performance of computer systems, or in order to increase the performance of processors like CPU or GPUs, we need to know the detailed architecture or detailed behavior inside of the computer systems or processors like GPU or CPUs. Okay, and then it's same to the storage devices. To study for some performances or reliabilities, what's that? The cost of the storage devices. We need to know the detailed characteristics of storage systems. Okay. So in today's class, we will learn about the characteristics of flash memory. Okay, because the flash memory is a main storage media inside of an SSD. So we need to know the characteristics of flash memory in order to understand the behavior of SSD firmwares or flash management functions inside of this SSD firmware, and then some other performance issues in an SSD. Okay, and then also the flash memory is a kind of non-volatile memory. So that means that this data inside of the stored in this flash memory is not erased, even though power is turned off. So that's why the flash memory is used for storage media. Also, this kind of memory can be used for persistent memory. And then usually many industries, like many companies, and then some lots of academic research institute focus on this non-volatile memory. It is because we can use this non-volatile memory for the high density memory, even though the performance can be lower than the conventional volatile memory, like main memory, like DRAM, but the density can be higher. Also, we can store the persistent data inside of this non-volatile memory. So why persistent data is so critical to the computer systems? Because if this data is maintained even the power is off or some crashes inside of the computer systems. So and then if this kind of crashes happen, then we need to recover the corrupted data or some lost data in the computer systems, and then it will take a very long time. Also, the cost for this data recovery is very high. It's actually in the server systems or some cloud infrastructure. So if this data can be stored in the non-volatile memory persistently, then we can recover this data more easily. That means more easily, and then we can reduce the cost for data recovery. We can also protect some user data inside of the cloud or some server systems. So that's why the non-volatile memory is so critical. And then this is the new kind of memory. And then also non-volatile memory has some better characteristics compared to the volatile memory, like density. So we are focusing on some non-volatile memory, and then many researchers are focused on these non-volatile memories. Okay. Okay, let's start. So this graph shows some semiconductor market trend. So actually so I Googled the semiconductor market trend graph, but this graph is studied before COVID-19 pandemic. So maybe this data like 2020 or 2021 data may be different from our current data, but this data is these numbers are some expected number. That means the expected data. But we already know that the semiconductor industry is very important to every nation or every country, because semiconductor is leading the electric device market. Also, as you know, the semiconductor industry leads some other markets such as car industry or some other yeah, every industry is even though, so you know that because of the some supply chain of this car semiconductor industry, so it is very hard to get a new car from the some what's that? It's a vehicle vendors. Okay, so that's why the semiconductor industry is very critical. And then as you expect, uh, and then this semiconductor market increases continuously. So you know, this is the overall market size of the semiconductor market. And then as you can see, the graph increases continuously. And then also this semiconductor market includes the many different kinds of chips. That means the many different semiconductor chips, such as the general purpose processors, some special purpose processors like AC. So it includes the memory devices like most memory. But as you can see, the non-memory devices such as the ASICs or processors have the larger market. So that's why the system ICs or some system the processor market is also very important and very critical for these semiconductor markets. Okay, but as you can see, the memory market, so memory market size also increases continuously. Okay? And then, as you know, South Korea is leading the memory market. Okay, memory device market. So let's focus on the memory market trend. As I explained, the size of the memory market also increases continuously. So this is also the expected number for the DRAM market. And then as you can see, the size is increasing continuously. But let's focus on the NAND flash market. Then so this graph shows the size of 2D and 3D NAND flash market. And then actually in the late 2000, the market size is smaller than the DRAM market. But then it is expected that the market size is similar to DRAM market size. So market size of the NAND flash, it is expected that the market size of the NAND flash memory can be similar to the market size of DRAM. Okay, so what does that mean? So a large amount of the NAND flash memory will be used for the computer systems, and then actually, this the market size means that the very large amount of memory like DRAM. So we already know that the DRAM is it's a necessary part inside of the computer system. Actually, every computer system requires DRAM. It is because the DRAMs are used for main memory of the computer system. But as you can see, the size of the flash memory it is expected. Is it just the expectation? But the market trend is expected that the size of the NAND flash market can grow similar to the market size of the DRAM. So that means the NAND flash memory can be a very critical part of our modern computer systems. Okay, So that's why. So we are focusing on the storage devices or some persistent memory systems and for the future computer hardware or computer systems. Okay. This kind of research is very important for the some for so modern computer systems. Okay. And then, as you know, the DRAM market is led by two big companies in South Korea, Samsung and SK Hynix. So Samsung and SK Hynix occupies the nearly 75% of the entire DRAM market. So that's amazing. So actually, the two companies in South Korea occupies the 3/4 of the entire DRAM market in the world. So that's why the Korea in the South, the industry in South Korea is led by the semiconductor industries, but actually it's true that but so usually the DRAM market decides some market trend of the market environment in the South Korea. Okay. And then let's focus on the NAND flash memory. So actually, say Samsung is the best company also for the best company for the NAND flash memory. So that means that the Samsung occupies the largest portion of the NAND flash market. So also as you can see, SK Hynix is also occupies the nearly 12% of the NAND flash market. So also these two companies also lead the NAND flash memory market too. so these companies have strengths in the memory industries or memory market. And then usually actually, I don't know about the Kioxia. It's some like I think it's actually Toshiba. So Toshiba NAND flash memory in the company. So it is sold to the other some consortium, and I think it's a Kioxia. It's hard to pronounce it. And then WDC means the Western Digital. It's actually SanDisk. So these companies are also occupies about more than 30% of the entire NAND flash market. Then Micron and Intel, some other companies. So this NAND flash market is also critical and then very important in actually to the students and engineering students in South Korea, because these two companies are leading the memory market in the world. Okay, so let's see the category of the memories. So we store our data inside of the memory, and then we can categorize this memory to the two kinds of memory devices, such as non-volatile memory and then volatile memory. So in the undergraduate course, we learned that the representative memory for non-volatile memory is ROM, that means read-only memory, and then the volatile memory is RAM, the random access memory. Then we for this random access memories, we use DRAM and SRAM, and I believe every student knows how the DRAM and SRAMs are different. So what is more expensive? The SRAM is more expensive because SRAM means 6T, so usually 6T. So T means the number of transistors, and then DRAM usually requires 1T and capacitor for the memory cell, for every memory cell. And then as I explained, the data inside of the volatile memory is erased if power loss happens. but the data in the number the memory is not erased. Okay, and then there are different kinds of memory, like it's a ROM, and also we can split this number the memory into ROM and hybrid memory. I don't know why it's called the hybrid memory, but I think it's the it is categorized based on the some energy for erasure. Okay, so there are several kinds of non-volatile memories such as Eep Rom, flashy, and Eep Rom. So we will learn about these different kinds of the non-volatile memory briefly in this today's class. But the energy for eraser is very high. It's very high. So actually we need the ultraviolet light wave to erase the data inside of the EEPROM. So it's a very high. And then also the required energy level for erasing the data inside of the EEPROM is also high, but we can use the electric signals. Okay, so we can use the electronic energy, electric signals to erase the data inside of the EEPROM, and flash memory is the same. Actually, the flash memory is the kind of EEPROM. So we need the electric signals to erase the data inside of this hybrid memory. Okay. So this is some memory categories. And then, okay, and then let's learn about the EEPROM. So EEPROM means the erasable programmable ROM. So erasable programmable ROM. So when we mention the read-only memory, this data stored in conventional ROM is not erasable. It's like actually the structure of the ROM looks like it's a word line, and then it's a bin line, and then just to connect each word line and bin line. So this is it's a permanent connections between word lines and bit lines inside of the ROM, read-only memory. And then this connection is a permanent connection. So we cannot erase the data inside of the ROM. Its data is not erased. So that means that the data is maintained nearly forever, nearly permanently. So the reliability is very high, but we cannot modify the memory. We cannot modify the data inside of ROM. But EEPROM means erasable and programmable ROM. Okay, that means the data can be erased. And then also for this operation, we have each memory cell of EEPROM has, what is it required? Switch. Okay, so actually the CMOS transistor. So transistor is the definition of a transistor is the electrically controlled switch. Okay, so as you can see, this is some basic structure of this part of the EEPROM. And then actually when I explain about the structure of the ROM, the word line and bin line can be connected. If this word line is connected to bin line, that means 1 or 0. So one of the values can be stored inside of this memory cell. And then, so not to implement this structure, we need the switch. So it's a switch like the lamp switch or like so. So if we push the on part, then the wire is connected, and the off part of the switch, then wire is disconnected. And then this is the same to the memory cells, actually, memory cell of the ROM. So the word line and bin lines are connected like here, and then these connections are controlled by some data stored in this memory cell, each memory cell. And then in order to implement this controlled switch, the Eep Rom has the MOS transistor-like structure. Okay. So this structure is very similar to MOS transistor, but unlike the MOS transistor, the electrons can be stored in this gate. Okay. And then this gate is called the floating gate. So in the traditional MOS transistor, if the gate, if we control the gate voltage level, then the channel is generated between source and drain, and then through this created channel, the electron channel, then electrons can move from source to drain or drain to source. That's how the switch functions are implemented using CMOS MOS transistor, not CMOS, MOS transistor. And then it's the same to the actually erasable ROM. So there is the floating gate, and then electrons can be captured inside of this floating gate. So if the electrons are captured, then the holes, like the positive elements, are move, the density of the holes increases between source and drains, and then these holes or some positive like elements hinder to create the electron channels. Okay, then interfere to prevent from creating the electron channels. Okay, so that's why if these electrons are captured inside of this floating gate, then the channel is not created, even though the gate voltage is induced to this transistor. It's a little bit tricky, so it's because it's similar to the it's like a semiconductor devices. So it's very low level, but try to understand. Okay. Actually, we learned about this behavior of transistor in the very basic undergraduate course, like data logic design. I believe I did not teach the data logic design course in Korean University at Korea University, but I taught the course at the other universities. Okay, so the captured electrons decides the data stored in this memory cell. If the electrons are captured, then that means the data 0 is stored, and then if the electrons are released from this floating gate, then data 1 is stored. Okay, but the Eep Rom, not Eep Rom, for the Eep Rom, erasable programmable ROM, in order to release electrons captured inside of this floating gate, we need very high energy level. Okay, high energy level. So these electrons are released from the floating gate, but we need very high energy level. So we need to use the ultraviolet light wave. Okay. And then for the write, how can we write the data? In order to write the data, this floating gate need to capture electrons. Okay, so there are many electrons here, and then in order to write the data, we need to capture the electrons to this floating gate. How can we capture electrons? So electrons have negative charge, and then in order to pull negative elements that have negative charge, we need positive voltage. Okay, so in order to write the certain data in this Eep Rom memory cell, we need very high voltage, positive voltage level. So if a positive voltage level is induced to this floating gate, then electrons pass through this insulator. Actually, this is insulator, but this insulator is very shallow. That means the thickness is very low. It's just very shallow. So electrons can pass through this insulator layer. If this high positive voltage is induced to the floating gate. So if with this high voltage signal, we can capture electrons inside of a floating gate, and that means it's right. Okay, and then if the data is written to this floating gate, that means the bit data 0 is stored inside of this memory cell. And then if data is erased, that means that the data 1 is stored inside of this memory cell. So if these memory cells are erased, then these memory cells have all ones for this all ones. That means the all data is 1, and then we can write several 0 data, and then we can write the data to the memory cell of this Eep Rom. Okay, so this is the basic operation of most transistor based storage devices. That means the storage media. Okay, the most transistor based persistent memory. Okay, so we can use the various memory devices for the persistent memory, like memnistor, STRAM, so I forgot the real name of this memory, STRAM, Spintronics. I think it's the Spintronics, STRAM or PRAM, like that. So actually the baseline characteristics of this persistent memory is different, but in this course, I just explained the most transistor-like persistent memory. Okay, it's flash memory actually. So this erase operation is critical actually. So for this Eep Rom, we need the ultraviolet light waves. Okay. So this UV rays cause the negative charge to return to this substrate of the memory cell. Okay. So we need a very high energy level. So if you so this is the very old type old chip. So if you see the top view of the Eep Rom, then this was that. Actually, the memory cells are revealed to the outer world. So that means that we can see the memory cells here. Okay, why? Not to erase the data inside of this Eep Rom, you need to induce ultraviolet rays to these memory cells. Okay, that's why this is glass, and then the inside under the glass there is a real semiconductor memory cells. Okay, so this is also another photo of the Eep Rom. So for the Eep Rom, we can erase about 1,000 times. So we can erase and reprogram the contents of the Eep Rom about 1,000 times. And then actually the Eep Rom has very high reliability. So that means that the data stored in this Eep Rom is maintained, is kept for very long time. Okay, why? Actually, the reliability is proportional to the energy for ratio. Okay, so what does erasure mean? The data is just erased, so that means that the data is lost. So if the energy for erasure is very high, then the data will be kept, even though some high energy level is given to these memory cells. So that means that the data is very high durability to the outside energy or some outside event. Okay, so that means that the reliability is very high, but problem is that in order to erase the data inside of Eep Rom, we need very high energy. That means we need very high cost. Also, the speed is very slow. That's the problem. So we developed the Eep Rom. So that's the electrically Eep Rom. So what is the definition of Eep Rom? That is erasable and programmable. So Eep Rom means that electrically erasable and programmable. Okay, so instead of using ultraviolet rays, Eep Rom, we can erase the data inside of Eep Rom using electric signals. It's a very high voltage actually. Okay. So, and then the basic behavior or basic operation is the same. So this is the the vertical structure of the memory cell of Eep Rom, and then as I explained, so this memory cell has the MOS transistor-like structure. Okay. So actually, the MOS transistor, there are sources and drains, and then poly is here, and then the gate is connected to this poly, and this is the structure of the MOS transistor. And then also the Eep Rom has the floating gate, as I explained for the Eep Rom. So this is, as you can see, this floating gate is composed of isolator. This is actually insulator. The insulator means that the electrons can pass through this insulator. Okay, isolator is here, and this is the floating gate. This is the floating gate, as you here, and then this is control gate. Okay, so it's just similar to gate of MOS transistor. Okay, and then electrons can be captured inside of this floating gate. So usually these are the insulators. So electrons cannot pass through to this floating gate because these are electrons. But if the high voltage is given to this floating gate, then electrons can pass through this isolator and insulator, and then can be captured in floating gate. The insulator cannot pass through this control gate because there are another insulator between control gate and isolate. So that means that electrons are captured inside of this floating gate, and then this floating gate increase the threshold voltage of transistor. Okay, so what does that mean? In order to turn on, so I think in the previous slide I mentioned that these captured electrons hinder, so that means prevent from creating electron channels between source and drain. Okay, that means that if the electrons are captured inside of this floating gate, threshold voltage of this cell increases. Okay, that's why we can store data inside of this floating gate. So why this is important? What is the basic behavior of CMOS MOS transistor? Since the CMOS means the complementary MOS, and then actually the MOS is a MOS transistor. Okay, if the VG, so it's a gate voltage is higher than threshold voltage, that means it's on, it's turned on. And then if the VG is less than threshold voltage, that means off. That's why the MOS transistor is voltage controlled switch. And then why floating gate is important? So why can we store data inside using the floating gate inside of the Eep Rom or Eep Rom memory cells? Because based on the amount of electrons captured inside of the floating gate, we can control threshold voltage. And then if the threshold voltage is increased, then with a certain voltage level, so gate voltage, the gate voltage is here. Even though, so for example, the gate voltage low, if the gate voltage is given to this gate, then if the threshold is very high, then it's always off. And then if the gate threshold voltage is low, then it can be controlled by gate voltage. So it can be turned on or turned off. So based on this different behavior by gate voltage level, and then different threshold voltage by the amount of captured electrons, we can store data inside of this floating memory cell permanently, not nearly permanently. Okay, we can implement the persistent memory. Okay, that's how this erasable and programmable ROM works for the non-volatile memory. Okay. What's the benefit of the EEP ROM? So because we can use the electric signals for controlling write and erase, then it's easier than, so we can use the EEP ROM more easily. So actually, to erase the data inside the EEP ROM, we need ultraviolet rays. That means we need the very special devices to generate the ultraviolet light waves. But for the EEPROM, we can just induce very high voltage in order to erase a certain memory cells. Okay. So it's a very convenient, because we can use the electric signals, and then also the data inside of the EEPROM also can be maintained for about 10 years. It's similar to the main durability of the EEPROM. Okay, but it's more expensive. Now, what is flash memory? So actually, the basic behavior of flash memory is same to the EEPROM. But why is it called flash memory, not EEPROM? Because with the flash memory, we can erase very quickly. We can erase data very quickly. So that's why this memory is called flash memory. So flash means, actually flash means means very quick or very fast. So with the flash memory, we can erase the data inside of the ROM very quickly. So that's why it is called flash memory. But the basic behavior, so that means the basic, the transistor behavior inside of the flash memory cell is actually the same to the behavior of EEPROM. So same floating gate principle is used, and then also some writability and then storage performance is also, because of the same floating gate principle is applied to the flash memory, then the write process or erase process can be performed using the same mechanism. Okay. But we need to focus on the energy level. Energy level for read, write, and erase. So actually for read, we just need the some low voltage. So it's a conventional voltage level, right? So it's a low voltage. So energy level is low. And then for the write, so in order to write the data inside of the display memory cell, then electrons need to pass through the insulator layer, and then these electrons need to be captured inside of the floating gate. So usually we need higher voltage level to write the data in the flash memory cell. How about the erase? So for this erase operation, these electrons need to be released from the floating gate level. How can we release these electrons, the captured electrons? At the very high voltage, the high positive voltage level is induced to the substrate of this MOS transistor cell. Then these electrons can be released from the floating gate. So for this erase operation, we need very high voltage. What does that mean? Read is relatively fast, right? It's slow. Erase is very slow. Okay. And so actually, in order to erase the data inside of the display memory cell, then very high voltage is induced to the substrate. So actually, there are many memory cells inside of the flash memory. So, and then actually the substrate is connected. So it's a common base of the semiconductor. So the very high voltage is induced, then this high voltage also influences other flash memory cells. So that means the data that this high voltage is induced for a certain cell, and then this erase signal may erase the neighbor cells, the data inside of neighbor cells. That's the problem. So why the erase is performed at block granularity, not page granularity. So we can perform the read and write at a page granularity to the flash memory, but for erase, we need the erase is performed at a block granularity. It is because we need very high voltage level to the substrate. Okay. Okay. I already explained about this floating. The basic idea inside of the floating. It's a floating gate. So actually, the idea of the floating gate is similar to that means the structure of the single memory cell of the flash memory is similar. It's nearly same actually. So it's similar to that of Eep Rom. So it's composed of control gate and then floating gate, and the electrons are captured inside of the floating gate. With this amount of based on the amount of captured electrons, then we can adjust the threshold voltage of this one MOS transistor. Okay. So also I compared the flash memory cell with the MOSFET cell because it's the same actually. The flash cell has the same structure with the Eep Rom cell. Okay. Okay. So let's take a break for 10 minutes and then I will be back in 10 minutes. So at 11:40. Okay. We are learning about some basic cell structure of flash memory. You may think that it's similar to it's a kind of electrical engineering course because we are just going down to the some device level of the each flash memory cell. Then also we are learning why the flash memory, how flash memory works, and then how this flash memory cell. So the main behavior such as read write laser can be performed inside of each flash memory cell. So in order to understand the behavior of flash memory, but we need to understand the behavior of each memory cell briefly, not deeply. So yeah, so you may think that also, it's very tricky because we are learning about device structure. But try to understand. Actually, the research starts from understanding the unique characteristics of systems, and they not to understand the unique characteristics of a system. Then we need to understand some basic behavior of some basic component. So what is a basic component of memory devices? It's memory cell. So for example, the DRAM. So in order to understand the behavior of DRAM, we need to understand actually briefly, not deeply. I mean briefly, we need to understand some baseline knowledge and the behavior inside of each DRAM memory cell. Okay, so why do we need the DRAM refresh? Why do we need column and column selection or row selection? Why do we need the row buffer? And then why do we need some DRAM controller to access data inside of the DRAM? So those are entirely related to the unique characteristics of DRAM memory cells. It's same to the flash memory. Flash memory is a solid state memory, and then it has a unique characteristics. So then in order to manage these unique characteristics very hard to pronounce it. So in order to understand the unique characteristics of flash memory cell, and then this knowledge is required for designing the flash memory, the flash management software, that is the flash management firmware inside of SSD. Okay, and then actually the various memory devices are being studied and it's being developed. So those memory devices are called the emerging memories. So as I mentioned, it's not fully commercially used, but many researchers are study on some various types of persistent memory, such as PRAM, memory stores, or STQRAMs. So these memories can replace some part of the DRAM or main memory or persistent memory. So we may build some new computer systems using these emerging memory devices. So, and then not to understand the behavior, and then in order for this study on the emerging memory technology, then we need to understand the the basic behavior, the basic characteristics of emerging memory cells, the underlying technology inside of emerging memory devices. So why we are learning about the characteristics and basic behavior of flash memory cells. Okay, so you may think that it's very tricky. It's not easy to understand, because some students are familiar with the programming, just programming, like the high level languages. So programming with the high level language. So so it's a very low level of the system. Okay, it's a device level. But for research, we need to understand some this device level also. Okay. Actually, the many papers are published for this regarding the unique feature of flash memories. Okay, because as I mentioned, the flash memory market grows very quickly, so grows very fast. So that's why the study on the flash memory is so important. Okay. Also, as I mentioned, in South Korea, two major companies, Samsung and Hynix, is Hynix focused on some semiconductor, some memory research, like DRAM, flash memory, and emerging memory technologies. Okay, so it will be very good for you to understand some basic behavior of these memory cells. Okay. So let's continue. So I already explained that the write operation to the flash memory cell is just adjusting the threshold voltage of a target cell. So actually, with this high voltage, the electrons can be captured inside of a floating gate, and then the amount of electrons captured inside of a floating gate decides the threshold voltage. So this is the off state, and then this is the on state. So that means the large amount of electrons, like the minus electrons, are captured inside of the floating gate, then the threshold, the voltage increases, and then that is the off state. So always off state, that means the always off state. So the lead voltage, so it is called the V lead, is given to a certain flash memory cell, but this lead voltage is lower than the threshold voltage. So as I explained, that is the off state. Okay. So if the circuit is disconnected, that means 0 for the flash memory. And then erase. As the electrons are released from the floating gate, then the threshold voltage is decreased. So when the V read is given to the gate of the flash memory cell, so that becomes the on state, because the threshold voltage level is lower than the V lead, so lead voltage. Okay, so the circuit is connected, that means the 1. So like the Eep Rom, the erase means that all cells have 1s. Okay, all flash memory cells have 1s, and then the right means that a certain flash memory cell has 0s, or some, that means some flash memory cells have 0s. Okay. So this is the cell structures. So So some detailed structure of the flash memory cell. Okay, so as I explained, this is the control gate, and this is the floating gate, and then there are insulator layers between control gate and floating gate. Also, there are also another insulator layer between the floating gate and substrate, and then drains are connected to metal, and then the source is connected to the ground. Okay. Also, that as I explained, so for the right operation, we need a very high voltage to the gate. And then for the erase, the electrons are released from the floating gate. Then we need a very high voltage to the B substrate. Okay, and then the 0 voltage is given to the control gate. So it's a different operation, actually reverse operation for the so this program. So the electrons are moved to the floating gate, and then for erase, electrons are moving to substrate. Okay. And then there are two types of the flash memory. It's the NAND flash memory and NOR flash memory. So what is NAND? Why is it called NAND, and why is it called NOR gate? So it is because the connections, that is the structure of the flash memory cell, looks like NAND gate of the NMOS transistor. So that is called the NAND flash memory. And then if the flash memory cells are connected like most transistors, NMOS transistors of NOR gate, is called the NOR flash memory. Okay. So this is truth table of the NAND, and the NOR, and then logic gate, and then here, so here. So and they're based on, so just to remember this structure. So with the NAND gate, the NMOS transistors are serially connected from a certain voltage. So it's a source, and that is no. It's drain. Actually, source and drain are the same. A certain voltage, so it's the output, and then ground. And then with the NOR flash memory, the one gate, so I think it's right. So one gate of the is connected to a certain voltage, and then another gate, another part is called connected to the ground. Okay. Okay, this is connected to the output, and this is connected to the ground. So how the flash memory cells are structured using NAND gate topology and NOR gate topology. So this is the NAND flash memory. This is the structure of the NAND flash memory. Okay. So this is the source line. This is world line. This is the bin line. Okay. So if you see the structure of the NAND flash memory, these flash memory cells are connected serially like NAND gate. The NMOS transistor of NAND gate. Okay. And then each data is stored in each flash memory cell. Okay, like this, just serially connected. Then the structure of a NOR gate is very similar to the DRAM. Okay, actually, the structure of the NOR gate is similar to the typical structure of memory devices. So word line is connected to this transistor, and then another part. So this part is connected to the bin line, the another part is connected to the source line. Okay. It's the ground, and this is the some voltage can be read from pin 9, and then word line control the gate operation of this transistor. It's very similar to DRAM. Okay. So but how about the density? So this is the some top view of NAND flash memory cell. Okay, so this is word line. This is the these are the word line, and then this is so this control gate. These are control gate. Then one part is connected to pin 9, and then another part is connected to the source line. Okay, but this is the NOR gate. This source line is also connected, and then this word line is here, and then the pin 9 is here, and then the source line is here. So as you can see, the density. How about the density? The density of the NAND flash memory is higher than the density of the NOR flash memory. Okay, but this NOR flash memory is good for the random accesses because the structure of the NOR flash memory is similar to the DRAM. Okay, so actually the NOR flash memory is used for code storage. Okay, but NAND flash memory is exhibit a very high density because of this structure, and then also it requires the low power, and then also it exhibits the good endurance. So it's good for the storage level memory. Okay, so that's why the NAND flash memory is used for the main storage media of the SSD. So let's see how the NAND flash memory is organized. So this is the vertical section of the NAND flash memory. As you can see, this is the substrate, and then this the end wells. And then if there are two gates on this channel, and that means this is the flash memory cell. And then this is the control transistor. So this is also the control transistor. So one part of this NAND flash memory cells is connected to the pin 9, and then another part is connected to the ground. So if we just cut the flash memory, NAND flash memory cells vertically, then the vertical section of the flash memory looks like this figure. Okay, and then this is the structure of the flash memory cell. How about the NOR flash memory? So this is the structure of the NOR flash memory, and then so actually this part shares the ground, and then as you can see, the two flash memory cells share the ground connection, and then also this another end of the flash memory cell is connected to the pin 9. Okay, this is the NOR flash memory structure. But we frequently use the NAND flash memory because of its high density, and then low power consumption, and the higher endurance level. Okay, so this is the schematic view of the NAND flash memory, and then top view of, as I explained, the top view of the flash memory, and then it's a vertical view. Okay. So let's see the detailed structure of the NAND flash memory. So in this schematic view, we can find that these are the control lines. Okay, so this line is called the SSL, and this line is called the GSL. Okay. And then this control register control the connections between bit line, and then this transistor controls the connections between ground. Okay. And then with this word line, the flash memory cells are connected. So this vertical transistors, these vertical transistors connections are called the string. Okay, so there's the group of flash memory cells, and then control transistors connected to between bin line and ground. Okay, and then for this one word line, multiple flash memory cells are connected commonly. And then we call this is the page. Okay, so when we learned about the SSD architecture, then we briefly learned about some characteristics of a flash memory. Then we learned that for read and write, we can perform read and write to flash memory at a page granularity. What does that mean? With this common word line, the entire flash memory cells connected to this word line is controlled, commonly controlled. Okay, so when this word line becomes 1, then we can read the data inside of this flash memory. So what means that this is a read voltage, and then if we just give the write voltage to this common word line, we can write data to a certain page. Okay, so this is the page, and then these flash memory cells and control transistors are commonly share the substrate. Okay, as you can see here. So as you can see, multiple word lines are connected to the series of NAND flash memory cells here. So word line 0, word line 1, word line 2, blah, blah, blah. And then these cells share the common substrate. And for the erase operation, we need to give very high voltage, so V erase to the substrate. So the erase is performed at a block granularity. Okay, because the large voltage is given to each these most transistors. Okay, so in a schematic view, this is the page, this is string, and then as you can see, this is the block. Okay, so that's why we can so if we see this schematic view of the flash memory cells, then we can understand why the read and write is performed at a page granularity, and then why erase is performed at a block granularity. Okay, so So you may think, that, oh, how can we read the data from this NAND flash memory? Okay, so let's think about the behavior of the NAND gate. So this is the NMOS transistor, and then input signal A and B is connected to this NMOS transistors. So if A is on and then B is on, then its output becomes the ground, that is the 0 voltage. So another case, the other cases such as A is off, 1 over A, and or B is off, then it's the output becomes the BDD. That's the operation of the NAND gate. Then how can we read the stored data? Stored data inside of this a certain flash memory cell. Okay, how can we read data? So so not to read the data from the flash memory, then we need this pin 9 can be connected to this ground line. So that means we need to read the data from this pin 9. So when the data is stored, data is written, that means that the electrons are captured in the floating gate. That means off is 0. And then the data is erased, that means on is the 1. Okay, so how can we read the data? So in order to read data from the selected word, so this line, then first we give the select word line voltage for the target word line. So it's called the B target. And then the read voltage is given to the other selected lines. Okay. So B read is given to the other word lines. So as you can see, this is the voltage level, and then V read is higher than the V target. And then based on the threshold voltage, then this is the VTH for data 0. V threshold voltage for data equal 0. And then this is the VTH. So that means the threshold voltage for data 1. So in this structure, V read is higher than the VTH. 1, 0. Okay, understand? So V read is higher than this threshold voltage. So regardless of the data inside of this flash memory cell, these flash memory cells are connected, just connected, because the V read is higher than this threshold voltage. Now, how about the target? The target voltage is lower than the V read, and then the connections and then disconnection of this cell is determined by threshold voltage. Okay, so that means based on the stored data, this transistor can be connected, or this transistor can be disconnected. So these are all connected. The unselected transistor are all connected. Okay. And then these transistors can be connected or disconnected based on the stored data. Okay. So and then also SSL and GSL for gate of the SSL and the GSL is this B read voltage is given to the SSL and GSL. So these are also connected. Okay. So based on the this operation, we can read the data, or we can decode the off, disconnected, or on, so connected from the flash memory cell. Okay. And then program. So for the program operation, we just give the very high voltage level for a certain word line. Okay. So for the unselected word line, so we give the B pass, it's the pass voltage, and then for the selected word line, we just give program voltage. It's a very high voltage. Okay. Also, the GSL is off, and then SSL is on. Then and then we can program the some data. Also, we can program 0 or 1 for a certain cell. So this data is determined by the voltage level of the bin lines. Okay, we can give VCC voltage for a certain also word line, and then if we just give 0 voltage for this certain line, then the data is written. So data is written means that the electrons are captured inside of the floating gate. Okay. So for the read operation, we can read out data from these bin line. Also for this write operation, based on the voltage level of this bin lines, we can program the target flash memory cell. Okay. Erase. So for the erase operation, we just give the floating voltage to this SSL and then GSL, and then we give the erase voltage to the substrate of the flash memory cells. So these are disconnected, and then we just give ground voltage to the gate of the flash memory cells. So this is the bulk erase to the entire blocks. Okay. So these are disconnected, and then the high voltages are given to the entire block. Okay. This is the erase operation. So that's why. So if we just understand, if we can just understand the required behavior or required input signals, and then required electric signals for each operation, then we can understand why the flash memory has the different granularity for erase. That's why the flash memory is slow for the write operation. So why the read is relatively fast. Okay. Then so this is the photo view of the NAND flash memory chip, and then cell efficiency is higher than the 65%. Okay, and also there are memory cells here, and then there are some peripherals that to control the some data read and data write. this flash memory cell arrays, like it looks like it is similar to the sense amplifier of the DRAM memory cells. Okay, so flash memory cell also has the buffer, then page driver, then some analog circuits that control the voltage levels. Okay. So these are this figure shows some conceptual data structure inside of the flash memory. Okay. So as I explained, the flash memory is composed of page. Okay. Then actually in the previous slide, we learned how the flash memory cells work for read, write, and erase. And this is the conceptual view. So flash memory is composed of pages, and then multiple pages composed of block. Okay, so this is the pages, and then so the pages can be read. That means that the entire page is read from the flash memory cells, and then this read page is buffered inside of the register. Okay, and then if this data is stored buffered inside of the register, and then actually the page size is a large, like 4 kilobyte or 8 kilobyte or 16 kilobyte. So this data is serially read from this buffer, like, or register. Okay, serially read from the flash memory register. So this is because the data width, the data channel for each flash memory cell is about the 8-bit, like the DRAM memory chips. Okay, so the data can be read with this read clock from the flash memory cell, and then with this read clock, the flash controller read the data from this register with 8-bit. Okay, every 8-bit. And then, as you can see, the flash memory one page includes the error correction code. Okay, so some data, some cells of a single page are used for error correction code. Okay, so this is the data overhead for ECC. So that means that when the data is read from the flash memory, then ECC is also performed inside of the flash controller, and then this is also a necessary step for the flash memory. Okay. For the DRAM, we can apply ECC error correction code for the DRAM word. Also, sometimes the server systems employs the ECC DIMMs. Okay, you can also apply ECC code for the DRAMs, but some cheap DIMMs, like a personal use, these DIMMs do not have any ECC code. But for the flash memory, as you can see, this read and write process of the flash memory is more complex than the read and write process of DRAM. Also, the threshold voltage and the read and program voltages are very finely controlled. Okay, so it's not just on and off. So read voltage and pass voltage has the very different voltage levels, and then also the 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 behavior of this each flash memory cell is determined by threshold voltage in this flash memory, and then this threshold voltage is determined by amount of electrons captured in floating gate. So why do we use this graph? So this is the distribution of the threshold voltage. So it's not always, so that means that even though even though the write operation, after the write operation, this is the distribution of the threshold voltage. The distribution can look like this. Okay, so some cells may have the fault incorrect threshold voltage. Okay, so that means even though the 0 is written to a certain cell, when this data is read out from this cell, then the read out data can be 1. Now, in order to fix this error, the flash memory includes the error correction code. Okay, so it's not simple system. It's a very complex system. Okay, error correction code is also included in the single page, and then this is used for the error correction code. Okay, this is some conceptual view of the flash memory. And then this is the functional view of the flash memory block diagram. Okay, so like the DRAM, the flash memory is also controlled by flash memory commands. So like also this is the memory cells. Okay, and then the target cell access is handled by some other X, so word line address, and then some column or some row addresses. Okay, also as we explained, when the one page is read out from the flash memory, then this page data is stored in the register or buffer. And then this is also controlled by the flash memory controller. Okay. Okay, so let's talk about the SLC, MLC, and TLC. So SLC means the single level cell. That means that each flash memory cell can store 1-bit data. Then MLC means that multi-level cell. MLC means that each flash memory cell contains 2 bits of data. TLC means the triple level cell, 3 bits. Well, what does that mean? So how can we control the number of bits inside of a single flash memory cell? So when I explained about the floating gate of the flash memory cell, this VTH is determined by, it's a function of amount of electrons, captured electrons. What does that mean? This is the analog function actually. So when you learn about the digital circuit, then what is the benefit of the digital circuit? So that means that the benefit of the digital circuit means that a circuit is very simple. Then we can just understand the turn on and turn off by the gate voltage level of the digital circuit. Also, the level of charge, right? You are right. So with this digital circuit, technique, then this circuit is very it's an endurance to the noise. Okay. Then what is a multi-bit cell is that based on the amount of electrons captured in the floating gate, we can adjust the threshold voltage level, and then using this adjusted threshold voltage level, we can decode the amount of electrons in floating gate. Okay, so with the 1-bit cell, we can just distinguish these bit threshold level and then this threshold level, and that's it. How can you store 2 bits? In order to store 2 bits, we need 4 levels from 0, 0, 0, 1, 1, 0 to 1, 1. So that means the threshold voltage level is the distribution of the threshold voltage level look like this. To repeat, we need 8 levels. Fine. So this is the this is the SLC, the MLC, and TLC technology in the NAND flash memory. So what is the benefit of the TLC? Benefit is that, density, right? So we can store the more data in the single flash memory cell, so 3-bit. So TLC, so theoretically TLC can store 3 times of data in the same area. So benefit, so high density. What is the disadvantage? It's high error rate, right? Performance is also, performance also matters. So in the previous slides, I explained that this is just the distribution of threshold voltage. So that means that the error can, so even though the data is written, that means that it's programmed, the threshold voltage can be generated at this level. So that is decoded as 0. If the threshold voltage has more levels, then it's not easy. Okay. And then another factor is performance. So how can we distinguish this multiple threshold voltage level with the V read? Okay. So actually in this slide, we just use the V target. So this is the V read. So with this voltage, in order to read out the data from the flash memory cell, we just need to induce this V target. But in order to distinguish different threshold levels, like so 4 levels, we need to give multiple voltage levels to read the data from the flash memory cell. So it will take longer time compared to SLC. So why do we say, SLC is faster than MLC or TLC? Because of this operation. In order to read out multiple levels of threshold voltage, we need to give multiple target voltage for read. Okay, that's why the SLC or MLC or TLCs are slower than SLC. The performance is degraded. Okay, so this slide just summarize the characteristics of SLC. The endurance is about the 100K cycles, data retention 10 years, read latency. So you can find these values, these metrics. How about the MLC? Data retention, endurance, read latency, program latency. Compared to SLC, performance is degraded. And then the data retention time is also reduced. That is connected, that is related to the reliability of flash memory cells. And what does endurance means? So the erase count for a certain flash memory cell has limited, is limited. So usually we can say that we can just erase 1,000 times for a certain flash memory cell. Its number comes from the TLC. So that means a certain flash memory cell is erased 1,000 times, then we cannot believe the data stored in this flash memory cell anymore. So it is just, you can say that, oh, this flash memory cell is broken because the data cannot be stored. So this is another research topic in the flash memory actually. So it looks like that. So, initial when the flash memory is initially manufactured, the threshold distribution of the threshold voltage level looks like this. Okay, but after some erases, then the distribution may looks like this. Okay, so this is called wear out of the flash memory cell. So it's like a wear out of every physical clothing or some object. The flash memory cells are also worn out. Okay, wear out. So after some more than this erasure count, the distribution of the threshold voltage may look like this. Okay, that's why the flash memory cell has the limited erase count. So because the TLC has more threshold levels, the endurance is less count. So that means that the TLC has less erase count. The data retention is just 3 years. So that means that if the data stored in the flash memory, if the power is not provided, then the data is erased. So it's not permanent memory. Okay. So if we just detach the flash SSD from our computer system and then we just put the SSD on the inside of our drawer for 3 years, then all data is nearly all data. The data inside of this SSD is just lost, erased. Okay, it's not repressed. So because that is the disadvantage of the solid state memory devices. So in order to store the data, we just capture electrons inside of the floating gate, and then the depth of the insulator is very low, so it's a shallow. So the electrons can be lost from the floating gate. So that means the data is erased. Okay, it's not permanent. And then, as you can see, the read latency is longer for the TS, as I explained. The program time is also longer. So performance is very low, but density is 3 times of SSE. Okay. Now we are even use QSC. That means the 4 bits of data can be stored inside of a single flash memory cell. That means the BTH, the threshold voltage, has 16 levels. It's nearly analog, actually. It's nearly analog. Okay, but we know so we can expect that erase count, data retention year, or some little time or little performance, and write performance of QSC maybe lower than the TSC. Okay. And then also people are very smart. So in order to also increase the density of the NAND flash memory, so we learned that this is the top view of the NAND flash memory. So in the NAND flash memory, the many NMOS-like transistors are connected like this. So it's a 2D. It's a 2D view of the NAND flash memory. So that means the length of this connected transistor may be very long, and it will occupy some areas. And if we stand this connected most transistors vertically, then we can reduce the area occupied by these connected most transistors. It's called the 3D NAND flash. That's why it's called the 3D NAND. So it looks like this. Instead of this 2D view of the NAND flash memories, then we can just fabricate these NMOS transistors vertically. Okay, so it's very smart. Okay, so with this 3D NAND flash memory, we can also increase the density of the flash memory. Okay, so that means the flash memory technology is advanced continuously. Okay, so we can so actually flash memories are used for storage media, and then many researchers try to increase the density of flash memory. Okay, because flash memory, the property of the flash memory is much better than the property of hard disk drive, because this is the solid state drive and the hard disk is the mechanical storage devices. Okay, so we just focus on the density of flash memory, but it also raises many research topics such as reliability, performance, limited erase count, and so on. Okay, it raised many research topics. Okay, so I already know that. So this time we learned about the property of device level flash memories. Okay. So I think it's not easy to understand because it's similar to the device level study for transistors. Okay. But if we can, as I said, if we can understand the basic behavior or basic property of this device level of the memory systems, then we can develop some smart ideas. We can develop some. So as I said, so these advances in flash memory raises many research topics. So that means that many problems actually. So we can also study on this property of the flash memory set. So we can focus on the performance, reliability, and endurance of the SSD or storage media, because flash memory has its unique characteristics. And this characteristics is different from other memory devices or hard disk drives. And then also the flash memory market grows continuously. So it's a very important market. So that's why the flash memory research or SSD research is very important. Okay, so I will post some papers after this class, and then so please read the papers. Okay. Then I stop here. And do you have any questions? Okay. Thank you for your attention for a long time. It's a very long time. Okay. And see you in the next class. Bye.